In step 1, we're putting together or condensing and the entry molecule with acetyl-CoA. Right. It's a spontaneous reaction. And we have a point of control. So the delta G is negative. And that's a pretty big negative, if you remember last discussion about the delta G. So this, because we're breaking this high energy thioester bond. Remember we said this thioester bond, carbonyl with a sulfur on it, that's what I mean by thioester. Carbonyl with sulfur next to it, that's a thioester. Breaking that thioester bond is a high energy bond. So because our reaction gives off a lot of energy, it's going to be controlled. It's also the first step in the reaction, in the pathway. So it's a point of control. So in my little document camera, what I'd like you to do to start off with, this word is condensation. I have my acetyl-CoA right up here. Comes together with oxaloacetate right here. It's citrate synthase. I have a star in it because it's a point of control. So that's one that you want to remember. And I have what's it's inhibited by. So it's inhibited by our money molecules, NADH, ATP, and then a downstream product. Citrate synthase is the word, inhibited by NADH, ATP, and succinyl-CoA. CoA, this word?
Yeah, what's that word?
Citrate.
The citrate synthase.
Yeah, inhibited by NADH, ATP, and succinyl-CoA. Succinyl, S-U-C-C-I-N-Y-L. Succinyl-CoA. We're going to cover that later. That's a downstream, within the cycle, but it's a intermediate. So if you have a lot of it, we're not going to want this reaction to occur. 4 molecules, or 4 carbons plus 2 carbons equals 6 carbon citrate. We'll see later that those 2 carbons are these up here. Oh, yeah. So acid, 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 3 acids, and a tertiary alcohol.
And this one, the top 2 carbons stay.
Yeah. Yeah. We're going to show some experiments where we put some radioactive acetyl groups in there, and how, when did they leave, which round. And that's a pretty interesting experiment. Now, I didn't have room to do double arrows or single arrows, but we know that this is going to be a single arrow because it's the negative delta G. It's exergonic. So if you have the notes, you can see the structure of citrate if you have trouble reading what I have here. All right, I'm going to go back, and you can see the structure of citrate. This is that product there. So 1, 2, 3 carbons. Each carbon has an acid, and then that middle carbon, which is tertiary, has the alcohol. So again, from our LR talk, what's happening next? What's the next step? What's the next step?
Oh, yeah, mechanics.
Yeah, you're going to move that tertiary alcohol to secondary. So that's an isomerization, right? It's an isomerization. We have an intermediate that is a double bond. So just like you would do this in lab, what you would do is you would remove an alcohol and then remove water, put a double bond in, and then add water to put it in a different spot. So this is what we're doing. in this mechanism. I'm not going to ask you to remember that, but it's an isomerization. You don't just pop it off and pop it back on. There has to be some sort of mechanism. That's why I'm showing you guys this. So cis-aconitate is that intermediate. Another neat thing about this is citrate does not have a chiral center, because here this is the carbon that you would think would be chiral. It has one group, two groups, but here this group and this group are the same, CH2 and acid, CH2 and acid, so it's not chiral. So, but here, moving the alcohol from this carbon down to here, then this carbon and this carbon are chiral. So it only makes one of the four possible stereoisomers as the product for isocitrate. Let's go back. So we go from our citrate, we isomerize, and we move that alcohol down. We get isocitrate. Cis-aconitate is not starred. I don't expect you to memorize it, but it is isomerization. Citrate.
That cis.
I think it's aconitase, actually. I wrote down the intermediate for some reason. This aconitase is the enzyme. I don't know why I did that. ACE. I don't know. Maybe I was thinking about that intermediate when I wrote this down. I'm not going to have you memorize that. I only want you to memorize those enzymes that are under allosteric control. So we already learned one, right? Citrate synthase, that's the first one. And then the ones that we're going to be losing the carbon dioxide, those are the other two. So there's only 3 spots. Okay, let's go back.
The one before we enter
The oxaloacetate.
the one where we have like ribbon,
Oh, that is controlled, but that's not within the cycle.
it's not in the cycle.
But it's controlled, that's right. We're going to talk about that a little later. Okay, so the third step is an oxidation and decarboxylation. But what happens in here is we take our isocitrate and we're going to first oxidize it, right? We're going to take this and we're going to make the alcohol a carbonyl here. And so because we're oxidizing, we need an NADH. And then what happens is the enzyme takes this acid out as a decarboxylation. So this is controlled. We're losing a carbon dioxide. So isocitrate dehydrogenase is the controlled enzyme. So let's go back to our document camera. And we are going to make we're going to go from our isocitrate. Look, I underlined the carbon dioxide that we're losing, the acid that we're losing. It's not there anymore. Here, we have the carbonyl and the acid. So it's isocitrate dehydrogenase. That's that word. The inhibitors are ATP and NADH, and activators are ADP and NAD+, high levels of each. We lose an NADH and a carbon dioxide. And you can call this an oxidation and decarboxylation. The product is alpha-ketoglutarate, Glutarate.
The activator is
ADP, adenosine diphosphate. So you have one less. Plus, yeah. So those are indicators of low energy. Again, this is made up by me, so it's not perfect. Anything made up by me is not going to be. All right, so now how many carbons do we have? 1, 2, 3, 4, 5. We've lost one through carbon dioxide. So far, citrate synthase for putting together citrate, making oxaloacetate and acetyl-CoA into citrate. Second one that we need to worry about is losing that first carbon dioxide, going from isocitrate to alpha-ketoglutarate. Julie, do you have a question? No? Okay. I'm going to go back to the PC. We'll have time during the break to get down anything that we're missing. So right after that decarboxylation, we have another one. And so we're taking alpha-ketoglutarate. We're losing this carbon dioxide, this acid is carbon dioxide, and we're putting it together with a thioester bond with coenzyme A. This is an oxidation step. There's another oxidative decarboxylation, so we're going to reduce, because this is an oxidation going from oxidizing the coenzyme A. It had hydrogen on it, now it's bound to something else, right? So NADH. Remember what I said about thioester bonds? Are they low or high energy? High energy, all right? So we're going to use that energy in the next step. So the enzyme for this controlled step, carbon dioxide, is alpha-ketoglutarate dehydrogenase, and it's a complex. It's much like that pyruvate dehydrogenase complex in our pre-citric acid cycle. I'm not going to go through it in detail, but it has the same things, coenzyme A, TPP, lipoic acid, all right, and we get an NADH out of it, so it's a lot like that. So we'll go back to our document camera, and all right. So we already have this down. Again, it's another oxidation decarboxylation. We get out an NADH and a CO2. We put in an NAD plus and a coenzyme A. This is alpha-ketoglutarate dehydrogenase complex. That word is complex, that's poorly written. The inhibitors are going to be ATP, NADH, and succinyl-CoA, which is the product. So we're adding on to it, succinyl-CoA. The activators, surprise, surprise, ADP and NAD+, and here's our succinyl-CoA. I didn't give enough room to write. Yeah, but I can't make copies like that here.
What's the enzyme?
Alpha-ketoglutarate dehydrogenase complex. Yeah, succinyl-CoA, the product, is an inhibitor. So we have a lot of that one particular product. The reaction isn't going to go forward. So now we've lost 2 carbons. So now how many do we have? We have 4. We have 4 there. 1, 2, 3, 4. Because we've lost this carbon dioxide and this carbon dioxide. We're done with the controlled steps of this cycle, this pathway.
So steps 1 through 4 are controlled.
No, not step 2, not that isomerization.
So 1, 3, 4?
1, 3, and 4. Yeah. So the first step in the decarboxylations, that's what I want you to remember. Let's go back. So we have this high energy thioester bond. We are going to then use that energy to couple it to the phosphorylation of GDP. We're going to get GTP, which can directly give that phosphate to ADP to make ATP. So you can think of GTP as a friend of ATP. It's slightly exergonic, meaning that the energy given off by breaking this thioester bond is mostly used up by this phosphorylation. So we don't really get, overall, when you couple those two reactions, the ending, when you add those two delta Gs, the ending is only slightly negative. So we say this is the first energy yielding step because it's yielding a direct GTP or ATP. So I have written here that the exergonic, it's only negative 3.3 kilojoules. I looked that up. All right, so let's go back to our document camera. I don't know how to do this. Focus on that. So here we have our succinyl-CoA. We put in an inorganic phosphate and a GDP and get GTP and coenzyme A. You can call this either a hydrolysis or a phosphorylation, or both. We get succinate, a symmetrical molecule. And the enzyme is succinyl-CoA synthetase, succinate. Notice how that is a symmetrical molecule. Now what we're doing from here on is getting back to oxaloacetate, as I mentioned a couple times before. So I'm going to cover those all in one. I'm going to go back to the PC. So here's our succinate, our symmetrical molecule. Again, we want to get, comparing this to oxaloacetate, we have a carbonyl here and an oxaloacetate. That's the difference between succinate and oxaloacetate. So what we want to do is try to get some sort of oxygen on this carbon so that we can oxidize it. So the first thing we're going to do is put a double bond in. We need FAD as a stronger oxidizing agent in order to do that. Again, this is not under control. Then we are going to hydrate that. So we get fumarate. I like to think it's fuming mad because it has a double bond and needed that stronger oxidizing agent. It's a way to memorize it. And then we're going to hammer that with a mallet, no, with water, that double bond to get malate. You got to come up with weird ways to memorize these words. And so then you hydrate this carbon. And what's going to happen next once we have malate? We're going to oxidize it so that we can get our oxaloacetate back. We're going to oxidize this one to get the carbonyl. And when we oxidize, we need something to be reduced. And there we go. So let's go back and finish up. This is succinate dehydrogenase, fumarase, and malate dehydrogenase. I apologize for my childlike handwriting. Again, what's missing is the pre-citric acid cycle, which is just as important. All right, during our break, we can write more of it, all right? I want to go back to the PC and talk about it as a whole. Look what we're getting out of this. So I know this is busy, but let's take a look at these. This is pyruvate dehydrogenase complex, or pre-citric acid cycle. And then this is the citric acid cycle. And then what we're doing is our overall. So pre-citric acid cycle, we put in pyruvate, we get out acetyl-CoA, but we also get our NADH, and we've lost the carbon dioxide. In the citric acid cycle, we put in the acetyl-CoA, but we get out 2 carbons as carbon dioxides, 3 NADHs, an FADH2, and a GTP. I don't need you guys to, again, just like with glycolysis, I don't need you to I'm not going to ask you to write the whole reaction, but I'll ask you questions about how much we're going to get, how many NADs, how many FADH2s. We don't get any FADH2s out of glycolysis, right? So the overall is when you take the 3-carbon pyruvate, you're going to get 3 carbon dioxides, 1 from the pre-citric acid cycle and 2 from the citric acid cycle. You're going to get 4 NADHs, 1 from the pre-citric acid cycle, 3 from the citric acid cycle. You're going to get 1 FADH2 and 1 GTP. Now, how much energy are we going to get from this? Well, what we can do, because we are already in the matrix, we can exchange those NADHs, just like exchanging foreign currency for ATPs. And they've done this phosphorylation to oxidation ratio that they've determined for each NADH, you can make 2.5 ATPs. That mechanism makes 2.5 ATPs. That'd be a pretty cool experiment. But anyway, so it's just sort of an accounting. So here, this is not counting glycolysis, okay? We're just counting per pyruvate. So you turn those in and you get 10 ATPs. So 2.5 times 4 is 10. And FADH, sorry for the typo, FADH2, that only makes 1.5 ATPs. I find that interesting because a stronger oxidizing agent, that FAD, when you turn it in, you get fewer ATPs from it. That doesn't make sense to me, right? I would think that a stronger oxidizing agent will get you more bang for your buck, but it doesn't. So that goes counterintuitive to me. And I mentioned GTP makes an ATP. So if you add these together, you get 12.5 ATPs per pyruvate, or 25 ATPs per glucose. This is not counting glycolysis, so we have to add those in. And we'll do that later when we go to the electron transport chain. So overall, we get a lot. Yeah, that's a lot. But that's with turning those in. So again, we're using the citric acid cycle and the pre-citric acid cycle, which is the pyruvate dehydrogenase complex reactions. 1 pyruvate, 3 carbon dioxides, and it's oxidative decarboxylation steps that you lose carbon dioxide. You lose these 3 carbons through steps called oxidative decarboxylations. Those oxidations are accompanied by reductions, right? So we get NADH and FADH2, and we get a GTP. The carbons that we put in are not the carbons that we get out from the decarboxylations in the citric acid cycle. So remember, we started with 3 carbons from pyruvate. We lost 1 of them in the pyruvate dehydrogenase complex reactions. That first one, before we went on to that TPP, remember, we lost that decarboxylation. So then we have the 2 carbons, and we're going to show them in yellow. These experiments were done most likely with radioactive carbons so that you can see when they're coming out, the timing. So remember, the first step is to condense. And they found that when they condense, the carbons that you put in from the acetyl group are these 2. Okay? So what happens is the alpha carbon right here, this is the alpha carbon, not like alpha dog, the alpha carbon is numbering, actually attacks the carbonyl of the oxaloacetate from the enzymatic activity right there. And so here, this is going to be the first carbon that we lose, right? It's not the yellow ones that we put in as the acetyl, all right? So we lose that through our first oxidative decarboxylation. And then we lose the bottom one through our second oxidative decarboxylation. So we're not losing those. So really, those original carbons that we put in through our original acetyl-CoA are not lost until 2 or 3 turns of the citric acid cycle.